So now that we understand what is powering the sun, let's talk about the sun's interior. Well, any good model of what's happening inside the sun is only based on two ideas. That's it. That's all we put into it. We have the idea of gravitational equilibrium and energy balance. So first, gravitational equilibrium. The idea of gravitational equilibrium is that any point within the sun has to have balanced forces. Okay, so it's not going to be sinking or rising, it's going to be holding still, so all of the forces must be balanced. Well, as we look at any particular piece of the sun, so in this case we have this red piece of sun, as we look at the forces on this, we've got a few of them. We have the weight of the slab pulling down, so gravity is pulling on this mass, pulling it downward. We also have the pressure from the gas above. Gravity is pulling on the stuff above, causing it to press down on this red piece of the sun. Then the last force we have to worry about is the pressure from the stuff below. This stuff is going to be pushing out against this slab, against this piece of the sun. So the idea of gravitational equilibrium is that all of the pieces that are pushing down or going down have to be balanced by all the pieces going out. Now this pressure from the gas above and the weight of the slab, both of those are just caused by gravity. So it's gravity pulling that stuff in. This pressure that's pushing out, that is electromagnetic pressure, because of the motion of the particles pushing out. So really, we only have to worry about two pieces. We worry about gravity pulling stuff in, and we worry about the pressure pushing stuff out. Okay, so we've got gravity trying to crush everything, and then we've got pressure trying to blow everything apart. So the idea of gravitational equilibrium is that gravity pulling in and the pressure pushing out have to be balanced. Here is our first clicker question. What would happen to the size of the sun if the pressure increased? A, the size of the sun would decrease. B, the sun would increase. C, it would decrease for a time and then increase. Or D, it's going to remain the same. Go ahead and think about it and we'll discuss in just a bit. Alright, so if the pressure inside the sun increases, then the force pushing out is going to be greater than gravity pushing in, so it's going to have to expand. So the correct answer is B. It's going to increase. So what something that determines all of the different stages in a star's life is actually this balance between gravity and pressure. What's going to happen to the star if pressure increases? What happens if the pressure decreases? So, as we just saw in the question previously, if the pressure increases, the star is going to expand. If the pressure decreases, then the star is going to shrink. Okay, so remember this process. If pressures increase, the star expands. If pressure decreases, the star is going to shrink. This is the entire idea of gravitational balance, gravitational equilibrium. Now, the other thing we have to worry about is energy balance. The idea of energy balance states that whatever energy is produced inside of the sun has to be given off on the surface of the sun. Okay, so imagine some scenario where the core somehow suddenly started producing more energy than was being given off at the surface. Okay, then more energy is being made inside and not as much energy is being given off. You can see that this is going to lead to something bad. Okay, so either the star would have to heat up, or would have to expand, or would have to change in some way. Similarly, if the core suddenly started producing less energy than what was being given off out at the surface, then again the star would have to change in some way. Either would have to shrink, or would have to cool down, or something would have to happen because of that change. So the idea of energy balance is whatever is produced in the core of the star has to be given off at the surface of the star. So we know that the energy is going to be produced at the center, and then somehow it has to transport out to the surface. There are only three ways that energy can travel. This is as radiation, through the process of conduction, and through convection. The idea of radiation we've actually touched on previously. Radiation is where the energy is traveling through empty space as light. Light is carrying the energy for us. Okay, a great example of this would be the heat you feel from a fire. Okay, you don't actually touch the fire, but the light, in this case, mostly infrared light, is going to travel from the fire to you, and then you absorb that and warm up. Or another example would be a laser. Convection is a process where matter is carrying the energy. Probably the best example of convection is boiling water. If you've ever boiled noodles before and you've actually stopped to watch them as they're boiling, you may have noticed how the noodles bubble up and then they roll down and sink again. This is convection. So the idea is that we have it hot on bottom and cooler on top. On the bottom, the water is going to heat up. As it heats up, it expands, and as it expands, it becomes less dense. When it's less dense than the water around it, it's going to rise. Now, as it rises, it's going to get to cooler and cooler layers, and it's going to lose that heat and actually cool off. Now, as it cools off, it's going to become denser than the surrounding water, and when it's denser, it's going to fall back down until it heats back up, where it expands, becomes less dense, and rises. So we actually get these cycles, these convective currents going. This is the idea of convection. So in the process of convection, the matter itself absorbs the energy, becoming hotter, and then moves from one location to another location, carrying that energy with it. This is the process of convection. The last way to transport energy is through conduction. Conduction is where the energy travels through matter, but the matter itself does not move. Okay, a great example of this would actually be the pot, not the water in the pot, but the pot itself on the burner. Okay, when you put the pot on the burner, the only part that's actually touching the heat source is the very bottom. But if you come back a few minutes later and you touch the top of the pot, it's hot. That's because the heat has traveled through the pot, but the pot itself did not move. Okay, so the energy is traveling through the matter, through the pot, but the matter itself is not moving. This is the process of conduction. At least for me, something that helps solidify these ideas is this scenario. In this scenario, we have firefighters, which are acting as matter, and the water they're carrying is the energy. Okay, so the firefighters are like matter, and the water is like the energy. So what happens is they scoop water, and then they pass it one to the other down the line until they drop it off. Okay, so in this process, this is similar to conduction. So if you remember, in conduction, the matter itself doesn't move, but the energy travels through the matter. So, in this case, the firefighters are not moving, they're just passing the buckets of water one to the other until it gets dumped out. This is like conduction. In this next scenario, the firefighters scoop up the water, run over, dump it, and then run back to scoop up more water again. This is similar to convection. So in convection, the matter stores up the energy and then travels from one place to another. Just like what's happening here. The firefighter scoops up the water and then travels from one place to another to then dump the water out. In the last scenario, we have a firefighter with a fire hose. This is similar to radiation. With radiation, the energy travels through free space, no matter necessary. Just like a water spraying out of a fire hose goes from the fire hose out, no firefighter is carrying that water. So this is similar to radiation. Here is our second lecture quiz question. Which of these is an example of conduction? A, the heat you feel from the sun. B, water boiling in a pot. C, the handle of a spoon in a bowl of hot soup. Or D, a laser. Go ahead and think about it and we'll discuss in just a bit. Alright, which is an example of conduction? It is C, the handle of a spoon in a bowl of hot soup. So A, the heat you feel from the sun, this is radiation. Then water boiling in a pot was our example for convection. And then A, a laser, is also going to be radiation. But the handle of a spoon, so when that happens, you put just the bowl of the spoon, the front part, the scooping part, down into the soup with the handle sticking out. Then heat travels from the bowl of the spoon up the handle so that when you grab it, the handle is now hot, or at least warm. Okay, so the correct answer is C, the handle of a spoon in a bowl of hot soup. Now, based off of the ideas of gravitational equilibrium and energy balance, we think we understand what's happening in the interior of the sun. The interior of the sun has 3 different regions. At the very center is the thermonuclear core. The core is the region that is hot enough with enough pressure to have nuclear fusion. All of the energy of the sun is produced in the core. Surrounding the core is the radiative zone. The radiative zone is, through the radiative zone, energy is being transported as radiation. Now, before we said that radiation is where the energy is traveling without matter. So, does that mean that there's no matter in this region? Absolutely not. There is still tons and tons of stuff in this region, but it is more efficient as the energy to escape as light than trying to push through the matter. So the light, you can think of it as little photons, so little particles of light bouncing around, slowly jiggling their way out. Now, because of the amount of stuff through here, it actually takes a really long time for that energy to actually pass through the radiative zone. The last layer of the sun's interior is the convective zone. In this region, the energy is being transported by convection. At this stage, we have enough energy difference, enough temperature difference from the bottom to the top, that it's most efficient for the energy to be transported as convection. So we have the convection cycles within the convective zone. And then finally, it escapes at the surface and travels in free space. Now, it actually takes many 100,000 years for the energy in the core to finally make its way all the way out to the surface. That's because of all of the matter that this energy is trying to push through, and then once it hits the surface and transports as light, it travels very quickly. So we think we understand what's happening on the interior of the sun based off of our mathematical computer models, but we would like to actually test these ideas. One of the things that we can do to test our ideas is to look for sound waves. So the sun is actually vibrating. It's kind of like a seismic wave or an earthquake that we have on the Earth, but it's traveling through the sun. Well, as it travels through and hits the surface, this will then give us information that we can use to understand what's happening on the interior. Well, as we look at these vibrations, they confirm what we expect for the sun having a core, radiative zone, and convective zone. Something else we can use to help us understand what's happening in the interior of the sun is to look for particles made from nuclear fusion, specifically those neutrinos. So the whole reason that I brought up neutrinos earlier was for this. Now remember, neutrinos have very, very, very little mass, and they have no charge. So they actually stream through the sun without interacting strongly with it. So we mentioned that light takes hundreds of thousands of years to finally get through all the layers and then hit the surface and escape. That is not true for neutrinos. Neutrinos are not really interacting with any matter, so they actually go almost straight from the core to the Earth without slowing down at all. So as we detect the neutrinos, it gives us a glimpse of what's happening in the core almost right now. It's not exactly right now, it's more like 9 minutes ago, but that's a lot better than hundreds of thousands of years ago. So we started to look for these neutrinos. Now, because of how small these are and how weakly they interact with normal matter, we have to build very, very large detectors. So to give you a sense, this thing up here is the detector for the neutrinos, and these are the workers who are building it. So this thing is actually really large. The first one of these experiments ever to look for neutrinos from the sun actually used a cubic kilometer of water to try and find the neutrinos. Okay, this thing was really, really big. Well, when they ran this experiment, this was in the 1980s, when they first ran it, they found only 1/3 of the expected number of neutrinos. 1/3. Now, this caused a huge problem. Either the sun's energy is being created, 2/3 of it is being created by some other source that we have no idea what it is, or our models are wrong. Okay, so something is significantly wrong with what's going on here. Okay, so this was known as the solar neutrino problem. The problem with the neutrinos from the sun, solar neutrino problem. Well, after decades of searching and trying to figure out what was going on, we found out that it's our understanding of neutrinos that was wrong. Our understanding of the sun seems pretty solid, but our understanding of neutrinos needed to develop. Specifically, there are 3 different types of neutrinos. Now, that was actually already known. That wasn't a problem. But only one type of those neutrinos is actually created in the sun. So when we created our detectors, we only created detectors that would look for the one type coming from the sun. What we learned is that neutrinos can actually change what type they are as they travel through space. So they will oscillate. They'll cycle from one kind to another kind. Well, only one type is being created in the core of the sun, but by the time it travels from the sun to the Earth, it's had enough time that those neutrinos will have completely randomized into all 3 different types. So when we build detectors looking for all 3 different types of neutrinos, then we find the exact number that we expect. So in trying to understand the sun, it actually helped us understand more about some of the tiniest particles in the universe.